record. That worked. I feel so powerful. I did it all with my index finger. Good. So chapter 4 is on aromatic compounds. And we've already defined aromatic compounds as benzene and derivatives of benzene. And are there other compounds besides benzene that count that are called aromatic? Answer is yes, there are. I don't think we're going to run into very many like that. We might run into a couple in the heterocycles chapter, but that's about the extent of it. Benzene is certainly the most important and most maybe typical example of an aromatic compound. And you can imagine getting thousands and thousands of other aromatic compounds by swapping out one or more of the hydrogens on benzene for other groups. And those are the compounds we're talking about when we mention aromatic compounds. It's all that whole class of compounds. Nowadays, the professor walks into chemistry class and draws benzene like this, and or you see it in your textbook or whatever, and we don't think much of it. But we didn't always, it has not been since forever that we've known the structure of benzene. It was kind of a mystery for a long time. And this is no history of science class, and I consider myself also to be particularly weak at history. So it's not something I'm going to spend a lot of time on, but I think there are a few things surrounding coming up with the structure of benzene originally that are somewhat interesting. So I don't think it's a terrible shame if I spend a couple minutes on it. Given the tests that they were able to do back in the 18th and 19th centuries, at first, all they knew about benzene was its empirical formula, not molecular formula, empirical formula. So they knew that benzene's empirical formula was CH. In other words, they knew it had exactly as much carbon as hydrogen in it. And it was only sometime after that that they solved the molecular formula of benzene as C6H6. And that in itself is a somewhat interesting formula. One of the things that is fair game for this upcoming exam is this whole idea about molecular formulas and how molecular formulas have limitations on them in terms of what they can be. And one hard limit on any 6-carbon compound is 14 hydrogens. Remember your formula CnH2n plus 2. That tells you the maximum number of hydrogens that you can have given a certain number of carbons. Given a compound with n carbons, the most hydrogens you can have is 2n plus 2. So for a 6-carbon compound, the maximum number of hydrogens possible is 14. We've got 6. So that means we have 4, as they're called, degrees of unsaturation, or the index of hydrogen deficiency is 4, meaning 4 pairs of hydrogens. So we're missing 8 hydrogens in the molecule. And now we understand that's because of all the pi bonds and because of the ring. So we have the equivalent of 3 pi bonds in one ring. 3 plus 1 is 4. There's your 4 degrees of unsaturation, meaning that we're missing 4 times 2 is 8 hydrogens. So that accounts for that. But I showed you some examples of structures that they came up with that had the formula C6H6, but that are not benzene. It took them a while to come up with this structure that you see here that we normally draw like this, with a 6-membered ring and 3 alternating double bonds. But of course, now we understand that the double bonds aren't really double bonds. We understand that this is a resonance stabilized species. And there you go. Resonance is also fair game for the first exam. So you see how in any given chapter in this book, it's going to refer back to previous chapters. This class is cumulative. So this lecture won't be entirely a waste of your time. We're going to touch on some of those topics anyway. I can't help myself. It's just the nature of the material. But there is another resonance form for benzene, which looks like this. And again, let's not forget, this counts as part of review. Let's not forget what resonance means. Resonance is not an equilibrium. Benzene does not consist of 2 things rapidly flipping back and forth. Benzene has one structure. And that one true structure of benzene is at all times a mixture, a hybrid of those 2 structures. I believe I told you guys last time, if you think of benzene as having neither single bonds nor double bonds in the ring, but 6 equal 1.5 bonds, that would be a perfectly good way of thinking about benzene. That would actually make me rather happy if you thought about benzene that way. And that explains why benzene doesn't behave like an alkene. It's because it's not an alkene. So we do not have localized double bonds in benzene, like in cyclohexene or something like that. So that's why, although chemists were astonished at first when they discovered that benzene wouldn't react with any of those reagents you would learn about in chapter 3. What did we talk about? Addition of acids, right? HCl, HBr, and HI. We talked about hydration, addition of water. We talked about halogenation, which is addition of Cl2 and Br2. I feel like I'm missing one. I feel like there were 4 of them. Hydrogenation, right. And benzene doesn't react with any of those sets of reagents. You can take any of the reactions that we talked about in chapter 3 and apply them to benzene and you will get no reaction. And chemists were very astonished when they first discovered this. They even went beyond that and treated benzene with some things that are far worse than the reagents, far more reactive than the ones we talked about in chapter 3, like potassium permanganate, I think I mentioned the other day. Potassium permanganate will oxidize anything. It's one of the permanganate ion is one of the best oxidizing agents known to man, and it does not touch benzene. So something is going on here that's different. And I think some of that we will leave until Wednesday after our exam. We can talk about resonance energy and all of that stuff that day. I'll take you through it. There's some, on Wednesday, there's some numbers and some figures in your book, and I'm gonna take you through it just so that you understand what they're talking about. But our goal, as usual, is not going to be to memorize all those numbers. I'm really not interested in you spending a lot of time memorizing a bunch of numbers. I don't think that's a good use of your time. Good. So so much for that. So that's why lots of times you'll see, like, especially when benzene is hand drawn, you'll see it drawn like this quite often. I tend to draw benzene rings like that. You can do that if you want to when you're drawing structures. Like by hand, or if you'd rather draw benzene like one of those, that's fine also, whichever you prefer. That's perfectly fine for me to leave up to individual preference. Now, when you're working on OWL, you will need to draw a structure like this. Actually, I think you can draw a benzene ring in one mouse click, but you'll notice it comes out looking like this. Likewise, any structures I draw on exams or class handouts or anything like that, I will tend to be drawing benzene like one of those structures because I don't have a good, easy way to draw benzene with a circle in it. It's just, for some reason, it's very difficult to do in ChemDraw, as the program is called. It's not easy to draw it with a circle in ChemDraw. But these, just like on OWL, that's one mouse click for me. So that's the way I'll draw. That's the way you'll see it on exams and other class handouts. Good. So what else do I need to say about the structure of benzene? I think actually if we, let's see, I think I'll save nomenclature for next time just so we have some actual material. Maybe I'll just make sure that we're clear on other ways to write benzene. Writing C6H6 for benzene is also perfectly acceptable. That structure is, or that formula is essentially unambiguous. No one will think you mean one of those wrong guesses at the structure of benzene that I talked about the last time. Everyone will know you mean benzene. Benzene with one hydrogen missing, you can write C6H5 and then attach whatever it is you like for that 6th bond. That's fine. Perfectly acceptable to abbreviate a phenyl group that way. The definition of phenyl, geez, can't even write today. PHENYL is benzene without one hydrogen. So that's the definition of a phenyl group. Or in other words, benzene with one of its hydrogens substituted for some other group. We call that a phenyl group. And it's actually pronounced exactly the same that you can go to the grocery store and buy fennel, but that's different. You're putting that in, you're chopping that up and putting it in stews and things like that. Wrong fennel. This is also pronounced the same way though. And the phenyl group can be abbreviated C6H5. It can also be abbreviated pH. So when you see pH, please don't think we're making up a new element. It's a symbol for a phenyl group. So for instance, you could write chlorobenzene. We'll take care of all of the nomenclature stuff the next time. So chlorobenzene would look like this. pretty obvious name. You could also write C6H5Cl or PHCl. All of those are one and the same thing. They all refer to the same thing. I don't care whether you use pH or not. You don't have to use these abbreviations. If you prefer C6H5 to pH, go for it. It's never mandatory to use these abbreviations. All I ask is that when you see them, you understand them in any printed material. So now if you see something like that, you know what it stands for. I will say that if you have a multiple substituted benzene ring, like you have 2 or more groups replacing hydrogens, then pH doesn't work. You have to draw the structure out. I won't say I've never seen anyone try, but it's not correct. It's not best practice. Let me see if there's anything else I can think of to say. We're at 2:10. Goodness, there's still half an hour. Well, that's not a bad thing. I wanted to do a lot of review. Maybe there's just one more thing that I simply can't resist saying now. And that is because I don't know how much we're going to run into it, but I just want to help you guys with this ahead of time in case we run into it, because it's or for such time as we run into it. And it goes under nomenclature, which I'll leave most of the nomenclature stuff until Wednesday. But it's one of those unfortunate things, and it's this term benzyl. So this is a phenyl group. There's also such a thing as a benzyl group, and it's very confusing. It's kind of a misnomer. A benzyl group is essentially phenyl CH2. It's very unfortunate. It's confusing because you almost wish a benzyl group were the same as a phenyl group, but it's not. Benzyl group is phenyl with 1 more carbon. And so when they talk about a benzylic position, they're not talking about something attached right to a benzene ring. They're talking about something attached on the carbon next door to a benzene ring. It's unfortunate. The name is very, very old. I'm probably 150 years old or something like that. And we're stuck with it. But it's just one of those things that's confusing and unfortunate. So for example, just so you can see some ways that it's used, this compound is called benzyl bromide, as compared to this compound, which would be bromobenzene. Sorry, it's so tilted, but you see how that's confusing. When you first hear the words benzyl bromide, it sounds like it should be this, but it's not. That's bromobenzene. This is benzyl bromide. Or just to give another example, it's a very common alkyl group. This compound we would call benzyl alcohol. And I'm very sorry about it. It's just one of those things we're stuck with. None of us was around when they made up that name. We weren't able to protest, as I would certainly have been right there with you protesting that name. It's just unfortunate and it's confusing. So when you hear that word benzyl, just be aware that it refers to a benzene ring plus 1 more carbon. And the benzylic position is next door to a benzene ring, not directly attached to a benzene ring. It sucks, but we're stuck with it. Good. So I don't mind spending the rest of the time on review. I thought at least something I would do is make up some problems. I have a real sense that you would like me to go over the study guide with you. So I will do that. I've already made this available for you, lists out all the topics, or at least most of them. This, as far as I'm concerned, is, if not all, most of what we covered in class. I do want to point out that the other study guides that I made for you, I know I've said this before, but I just want to make sure I'm very clear. This study guide just so happens to line up with the first exam, because it's on chapters 1 through 3. The others will not necessarily line up with exams 2, 3, and 4. I've separated them by chapter, and so they're not too terribly long. And I've given you sample questions from old exams. but the others don't necessarily line up perfectly with the exam. So it might be that for some of the exams, you'll need to look at 2 separate study guides to see lists of all the topics. But I still did give you study guides. The only thing I don't have any material on, again, is the chapter on heterocycles, since we'll be doing that for the first time, and the chapter on polymers, which is the last one we'll do. That one will also be for the first time. So I don't have any questions from old exams on those, and I don't have any lists of topics from all those. But I've been, I think, pretty good about putting topic lists at the beginning of each chapter of class notes. In fact, I can almost guarantee what I did is I just flat out copy pasted all of those topic lists from the class notes. And I bet that's how I came up with these study guides. I bet that's all I did. You can find similar topic lists at the back of each chapter. I think their study guides are actually pretty good. So you can feel free to refer to those as well. But my general answer for all questions concerning what will be on the exam is you're responsible for everything in the book, especially if we covered it in class, unless I specifically said, either in class or in the class notes or in the syllabus, that you're not responsible for it. And basically, when in doubt, assume you're responsible for it. But I tried to be pretty careful about being clear in the syllabus and in the class notes when there was something you weren't responsible for. So if it doesn't specifically say that you're not responsible for it, then you're responsible for it. And I think that will answer all such questions in terms of what's going to be on the exam. Like I said, I don't plan on there being any surprises. At least I can guarantee you, if there are any surprises, they're not intentional. So we talked about atomic structure a little bit. We talked about electron configurations. We went over rather too many of them, in fact, but we did talk about that. The difference between ionic and covalent bonds is something that you covered in Gen Chem. I would expect you to be able to tell whether a compound's organic, meaning covalent, or organic compounds tend to be covalent, or an ionic compound like sodium chloride or potassium carbonate. Those are going to be ionic compounds. We talked a little bit about bond polarity and how to tell whether a bond is polar or non-polar. Traditionally, that's done with Pauling electronegativity values. I certainly will not accept, and I said this, that you will not have to memorize all those Pauling electronegativity values, but I do expect you guys to know the general trends on electronegativity. We went over that, and you can see those on the periodic table. We said that electronegativity increases from left to right on the periodic table and increases up the periodic table. That's an important trend. That's something we'll use repeatedly all term. So that means that the most electronegative element you're going to run into is fluorine. We don't include the noble gases because they're not forming bonds. Valence and formal charge, we went over pretty thoroughly, I think. We went over drawing structures, although that's something that you will, to some extent, learn by practicing. Resonance, certainly we covered heavily. And I mentioned structure drawing. We talked a little bit about molecular shape and hybridization. And also we covered that, I would say, to some degree in chapter 3. So I went back and did kind of a throwback on some of that VSEPR stuff. We said how sp2 hybridized atoms are trigonal planar, for example. So I expect you to remember that from Gen Chem. And we spent quite a bit of time going over the classification of molecules by functional group. I would certainly expect you to be able to look at a molecule you've never seen before and know what functional groups are present. So again, it's not just memorizing what we did in class. I expect you to be able to apply the information. Chapter 2 is on alkanes. So we talked about all these things for sure. We went over naming of alkanes and cycloalkanes, and also of alkyl halides. Because if you can name an alkane, you can name an alkyl halide. You already know everything you need to know from naming alkanes. Going from structure to name or name to structure, I always found it easier to go from name to structure than from structure to name, but you don't have to agree with me on that. Bear in mind, of course, your exam will be multiple choice. And I'll also throw out this other tidbit. I can tell you that every question on the exam will be one that I believe is fair. I can make you that promise. I will not put a question on the exam that I think is unfair. Everything will be one that I believe is fair, which is why I always say, I can't help you interpret the exam questions. Now, certainly stop me during the exam if you think you found a misprint. That's important. But if you're having trouble interpreting the question, assume it's not a trick. take everything the most straightforward, surfacey way possible. I do not purposely write trick questions. Sometimes I succeed at it in spite of myself, but I do not purposely write trick questions. Good. We talked a little bit about intermolecular forces. That's important for understanding why organic molecules do what they do, especially now that we're starting to get into reactions. That's somewhat important. Reactions of alkanes, there aren't very many. You've got combustion, you've got halogenation, and that's about it. There's not too much else. We went over what you needed to know about those. I think I was pretty clear in class. We talked about at least the cycloalkanes through cyclohexane, and we talked about conformations of cyclohexane, certainly, and also of smaller alkanes like ethane. So that's something we spent some time on. We talked about cis-trans isomerism in both cycloalkanes and alkenes. And we're also including the stuff on E and Z from chapter 5, since I think that makes the most sense in a discussion of cis and trans alkenes, as opposed to waiting for 2 more chapters and suddenly having to refer back. I think it makes more sense just to cover it now. Knowing about E and Z isomerism is also going to save us some trouble. That will still become important in chapter 5 when we get to stereochemistry. But I think it does no harm to mention it here. But we talked about naming alkenes and alkynes. And again, spoiler alert, if you know how to name alkanes, you've got at least 85% of what you need to know to name alkenes and alkynes. Remember that with alkenes, you might have the issue of cis-trans or EZ stereochemistry. Not always, but you might have it. Alkynes, of course, you don't have to worry about that. There is no cis and trans with alkynes because it's linear. So it's not an issue. What else? And this is where we went back and talked a little bit more about the VSEPR model and hybridization when we discussed the characteristics of pi bonds and sigma bonds. We talked about how alkenes undergo substitution reactions, and there's a small handful of reactions that you will need to know. I was pretty clear about what it means to know a reaction, that it doesn't simply mean memorizing the examples we did in class, but rather you should expect to be given alkenes you've never seen before, and one of the reactions we covered in class, and be able to predict the product. It also means being able to go backwards. Here's the product of a certain reaction. Here's the reagent that was used to make it. What was the starting material? Or you could leave out the reagent. Here's the starting material. Here's the product. What's the reagent that was used to make it? Also a fair question. But that's what it means to know a reaction. And that's going to be true the rest of the semester. It doesn't simply mean memorizing the examples we did in class. In fact, I don't know if I would recommend memorizing them at all. That might also fall under the category of something I don't think is terribly worth your time. We did cover Markovnikov's rule, and we talked a little bit about the mechanism of addition to alkenes. It's not something I'm going to emphasize very greatly, but since that mechanism is relatively simple and is only 2 steps, and they're fairly easy to understand steps, I figured it did no harm to do it at least there. And we talked about how you can use Markovnikov's rule to predict the major product when there's 2 or more products that are possible from an alkene addition reaction. And we talked about when that was. We said that's an issue when the alkene is unsymmetrical and the reagent that you're reacting the alkene with is also unsymmetrical. And so we talked about Markovnikov's rule and how you use that to figure out what's going to be the major product. OWL, you have to watch like a hawk. They might ask you to put the major product, or they might ask you to draw all possible products. So you have to read carefully the wording of the question. They're not quite as interested as I am in using language that's as straightforward as possible. I find if you read the instructions carefully, it's generally fair, at least most of the time, but you do have to read their instructions very carefully. And then we did spend some time on reaction equilibrium and reaction rate, reaction energy, and the types of reaction energy. And I'm really not interested in you memorizing any particular formulas. I don't think you would need them, but we did go over that so you can see how those all work together. And we talked about energy diagrams, how to set them up, how to interpret them, how to know how many steps are in a reaction, difference between intermediates and transition states, for example. All this was stuff that we covered the other day. So all of those topics are listed in your study guide, along with a few questions from old exams. I cannot promise those exact same questions will be on your exam. I would be shocked if there weren't ones that were at least similar. So, so much for the study guide. That leaves us at 2:25, which leaves us 15 minutes. I thought what I would do is make up, I don't know, 3 or 4 problems, let you work together on them for a little while, and then give you guys the answers. Is that reasonable? I mean, it's more productive. I know, okay, if you would like to leave early, you may leave early, but I thought it would be a lot more productive than just everyone leaving early. So let's see. What topics are you interested in? Maybe nomenclature is boring, but I should probably do one. Yeah, what, sorry? Naming, yeah, it's boring, but we should probably do one. Okay, so let's name, oh, let's go crazy. And I'll give you a hint on this one. Use EZ, E or Z in your name. I'll put a methyl group here. And let's put one of these guys over here. 8, 9, good. Oh, I just gave it away. That's fine. Let's just do one. I mean, I think they're kind of boring. Let's do maybe, oh, sorry. Oh, nothing, okay. Maybe some reactions from chapter 3. Is that a good topic? Or anything from chapter 2 that comes to mind? I figured probably reactions. That'd be a little cruel to use that same alkene. Let's use this one that was one of the wrong guesses at the structure of benzene. React that, please, with HCl. React it also with H3O+, that is H2O and H+, and then finally with Br2. And while I'm making up problems, let's do an example of one going in reverse. Oh, I know what I'll do. Oh, you guys will love this. There are questions like this on OWL anyway. I won't go too crazy. So this alkyl chloride over here is made by adding HCl across an alkene. I can think of at least 2 different alkenes that would give that alkyl chloride when you treat it with HCl. See if you can at least come up with one of them, but I can think of 2. And heck with coming up on alkene nomenclature, you've got an alkene. So this is naming an alkene over here. Maybe I'll also do a cycloalkane in case people are bored. There we go, I like that one. Name that guy too. While you do that, I know what I'll do. Watch this. Let's resume recording. Now it's on the video. All right, so I will see you all on Monday.